Hello everyone, this is Mohammad Abdulaziz and welcome to the 8th tutorial of the functional data structures course. Today we have two exercises concerning 2-3 trees. The first one, we're going to have to define a function that joins two to threes, two to three trees, and those trees are assumed to be of equal height. And what we want to guarantee is that the resulting tree maintains the same order of the elements in the initial two trees, and the fact that and the height of the resulting tree is also exactly the same as the height of the given two trees, or one. I'm sorry, yeah. So or one more. So the height of the two given trees or one more. Okay. So before we do that, let us quickly review the function that does insertion in those trees. Okay, so that is it. It's a little big, but I will just try and summarize the ideas with you on paper, and then we can investigate how we can extend those ideas to joining. So the first thing, firstly, when you're inserting in a 2-3 tree, what you're supposed to be, the outcome would either be that the element that you're inserting in the 2-3 tree was you were able to pack it in one of the two nodes, or you didn't find a two node where that element would be inserted, so there is an overflow situation. Okay. So firstly, a 2-3 tree is a tree that whose inner nodes have either one element and two subtrees, like this one. So this is an inner node, or has two elements, 1 and 2, and 3 subtrees. Okay, so this is a 2 node and this is a 3 node. Okay, so in case you're inserting, you can still in case you're inserting something, you can, for example, insert an element here in this node, and then it will become, if you want to insert 2, for example, it will become 1, 2. It can be, for example, that. Well, if you want to insert an element here, you can't do that, so you will have to reconstruct the tree. So the way this is done in the function that I'm showing you is by returning one of the two possible values. So let's say I will just do a sequence of insertions with you. So let's say we want to insert 1 and then 2 and then a 3 and build a tree that contains those 3 elements. So firstly, you start with a leaf. Okay, so that's all, which is the first case in the function. And then I want to insert the 1 in that leaf. So what we would return is that there wasn't a 2 node where the 1 could fit, so we would return an overflow. Okay, and because this is a leaf tree, the overflow would have a left tree of an empty tree and a right tree of an empty tree. So an overflow. Let me just show you the type of overflow here. An overflow like this type up I can be either an overflow like that. So an overflow is basically a left subtree, a right subtree, and an element, or a successful tree insertion, which is just one tree which is what happens when you are able to insert that when you find the place of the to insert the element without having to do an overflow. Okay, so anyway, and then after you insert that, the actual tree is, you obtain the actual tree by just applying this function. So here we apply tree I. If tree I given an overflow will construct the following tree. So you will have a 1 and then the 2 subtrees like that. This is after applying tree I. Okay, so that's the first insertion. Now we want to insert 2. Okay, so here we have, so here this is 1, okay, and that is 2, and we want to insert 2. So what happens is that the 2 is greater than 1, so you'd go to the right subtree. Okay, so you would have so you would basically end up with that situation that you go to the right subtree, and the right subtree is and you would go to the right subtree, and the right subtree is a leaf. So you would do exactly what I did here. So you would end up here you would end up with 2 and you would end up with an overflow of 2 and 2 subtrees like that. And then you want to combine that with this old 2 node, which is what resulted from the first insertion. So in fact there is space for us to add that to this node. So and the fact that the way you can do that is by getting the left subtree of the overflow and making it the set. So okay, so you extend the 2 node into a 3 node. Okay, so 1, 2 like that, and then you take the left subtree of the 2 node. It will be the left subtree of that, and then the middle subtree of the 3 node of the new 3 node will be the left subtree of the overflow, and so that would go there, and that would go there. Okay, and then if we want to add 3, 1 second. So then we want to add to insert the 3 like that. So you have a 1, 2, 3 subtrees. Okay. So here now we are in this case. Okay. So you have a 3 node, and you want to insert an element to it, and then we want to insert a 3. So we end up going into that case here. Okay. So you compare. So firstly, you compare the 3 to the 1. It's greater than, and then you compare the 3 to the 2, and it's also greater than that. So we end up trying to insert the 3 into this into the right subtree, which is a leaf. So you end up with a situation with an outcome like that is like that, and then an overflow like that. And then you want to combine this overflow with that 3 node. So you find that there isn't enough space for to fit this overflow, because this is already a 3 node. So so the whole outcome will become an overflow again. But you can either so you can do it that way. So you will split this and turn it into a 2 node again. So it will be like this. That's the left subtree of that overflow, and then the middle node of the overflow will be the 2. Okay, so this is there, and this is there, and then the 2 is there, and then the right subtree of the overflow will be that. Okay, so that is there, and that is there. Okay.
So that's basically how we do the insertion there, and as you have seen, we use this. The idea is that you either are able to pack the new element into an existing two-node, or you have an overflow. Okay. So let's go to the joining. So so you would do the same as what we did with the binary trees earlier in joining, the general idea at least.
You basically have two trees
okay, and then what you do is that because they are both of equal height, so you just will descend here until you reach the leaf, and then you descend there until you reach the leaf, and then you will try to make either this, the last node here, the root of the new tree. So you take this to make it the root of the new tree, and then you go up. Okay, so you would go return up those two spines that you descended on, and your goal will be that this would be the root of the new tree. So you either have that, and then this one is the right subtree, or you can do it also with the last one there instead. Okay, so you choose one of those and then you do that. But the way you implement it recursively and functionally is the following. So again, you will need to do this to use this overflow type, and you will need to consider each of the cases separately. So you basically define the function as follows: to be a function that is recursive in the two trees. So it will be so join. So let us consider like the separate cases. Okay. So firstly, when the two trees are leaves. Okay. So and then you want to join them. So basically, when you have reached the end. So the joining of two leaves should just be a leaf, okay? With and that should be a successful like there's no overflow here. So this should be a successful join. That means that it should be a TI, not an OF. So join the first let's check the types. So join the first one is a leaf and the second one is a leaf. It should return to us TI of a leaf. Okay, so that's the first case. The second case should be one of them is a leaf and one of them is not a leaf. But that case would never happen because the given two trees are both of equal height. So in fact we will just make our recursive pattern is not complete in the sense that we are going to just assume that both trees are not leaves, because that case will not happen because we're assuming that they are of equal heights. So the second case will be when both you have a two node on the left and a two node on the right, and you want to join those. So one way to join those. So what we would do here is that we will call. So you're here, and then what you would do is that you would call join on those two subtrees, okay? Like what we did earlier with joining on in the case of binary trees. So you descend this way, and then you will call join on those two leaves, okay? And then this will give you an overflow. Sorry, this will give you a TI, because in this case it's a leaf. But you'll need to consider the two possible outcomes. So maybe you actually have here trees, and then you will get an overflow. So you need two cases when you're given a node 2. So either the return of calling join here is an overflow or not an overflow. So firstly, let's deal with the case that it's not an overflow and it's just one tree. So basically, the return is here is ti of a tree. Okay, so that is the return of calling here ti of a tree. Then you would construct a 3 node of the two data elements there, and the left subtree will be that, and the right subtree of that thing will be that, and the middle subtree will be this t. Okay, and then you're done. The other possible outcome here would be if it is an overflow. So here you have an overflow of T1 and an element in T2. Okay, so you won't have 1, 2, and so you cannot fit those two subtrees and the original trees in one node. So you will need to return another overflow, and that overflow, one way to do that overflow is it will be an overflow, and the left subtree of that overflow will be 1, and then that left subtree will go there, and then the right subtree would be T1, and then the element of the overflow will be E, and the right subtree of the overflow will be 2 T2, and then this one will go there. Okay, so let us write the function that is equivalent to that. So join, and then node 2, and then L1, R1, L2, A2, R2, and then here you would do it cases. Join. So do the recursive call on the two spines, as I said, so R1 and L2, and then if that thing returns a proper insertion, then in this case we're going to return a 3 node with the left sub-tree L1 as shown in the paper there, and the first data element will be A1. And then the middle subtree will be T, and then you'll have A2, and then the right subtree will be L2. Okay. Out of case. Okay, so yeah, this should be a TI, not an overflow. Okay, and then in the second subcase, you have an overflow with a T1 and an A and a T2. Then in that case, we will again return an overflow, and as shown there, in the first subtree of that overflow will be a 2-node, so L1, A1, T1. Okay. Second subtree of the overflow will be T2 and L2 and R2, and the element of that overflow will be the A. Okay,
So that is equivalent to this case.
now let us consider the case when one of them is a 2-node and one of them is a 3-node, and the other symmetric case. So that's what we have here.
So let's say the first one is a 2-node. Okay. Okay, and the second one is a 3-node. Okay. And then you have a subtree like that, another subtree, and a third subtree. Okay, and then you want this way and that way. And then what you got, if you get, you'll have again 2 cases. First one is that you had a successful insertion, and that, so you called join on this subtree and that subtree, and then you got a successful insertion. So you have Ti and T, and in this case you're going to try to insert that tree, but there's no way you can construct a node that contains all of this, those 3 elements plus that tree, so you will need an overflow. So here you'll need an overflow, and then so the left subtree of that overflow can be 1, and then this thing will be as it is, and then the right subtree would be T, and the element in the overflow will be 2, and the second subtree will be 3, and this subtree there, and the subtree there. Okay, so that's the first case. So if you have a proper insertion. The other case, you could also have an overflow and a T1 and an element in the T2. And then in this case, you will need again to return an overflow, but what will the overflow look like in this case? So it will be, so you will have, for example, the one, like there are two, you need to return, in this case you'll need to return an overflow with one node, with one tree whose root is a 2 node and the other one whose root is a 3 node. So one possible way to do that is just one, and then you get the subtree of 1, and the right subtree of 1 would be T1, and the element would be that, and the right tree would be 2, 3, and then T2 here, and then the right and left subtree would be the same from that node. So that's one way. Of course, you can also just create a 3 node on the left here, and then the right sub. You can do the following: so overflow 1e, and then left T1, T2, and then the element would be 2, and then you would get 3, and then this would be a 2 node. But I will just go with the first case. Okay, so those are the two possibilities there. So go back to the function. So L 2 A2 I'll just call this M2, this is the middle tree, and then the element, the second element. So I'll just change these things to AB, okay, just so that I don't have to write many indices. So AB, and then this A and B, A, C, B, this case is right, okay. And then here this will also be A, and then you have a B, and then you have a middle tree, and then you have a C, and then you have a right subtree, and then you call the join on those two subtrees, and then if you get TI, you would return. So in both cases you return, as I said, an overflow. The first overflow will be with two trees whose roots are 2 nodes. So the first one here would be L1, T, and the element would be B, and the right one would be M2, C, R2. So that's the first case, and then the second case you return an overflow again, but one of the trees will be a 3 node. So you would return this would be T1, and then you have, that should be an A, that should be a D, B, C, D, and then that will be the D that we have there, and then node 3, the same node 3 there, but will be with T2 instead.
So that's one thing. And then this is the symmetric case where the left is a node 3. So M1, A, B, R1, 2, L2, CR2, and here this should be an M1. No, this should be no L1 and M1, and that should be a T. Just make sure this case is correct. Okay. And then here, the second case will be also the symmetric case, but we'll just have the node 3 in the here. So L1, A, M1, B, T1, B, T2, T2, and then C, and then R2. Okay, and that's the second case. When one of them is 2 and another one is a 3 node. The last case will be when both of them are 3 nodes. So in this case,
so here you have 1, 2, and then 3, 4, and then you call the function recursively here, and then you got a ti of t.
so here again there's no way we can fit all of that, like the 1, 2, and 3, and 4, and those 2 subtrees and those subtrees and this one in one node. So you'll definitely return an overflow. So you could either return overflow with the left subtree like that. So 1, 2,
and then a right subtree t, and then here 3, and then 4, and a right node that's a 2 node. Okay, so that's one way to do it. And of course there's other symmetric way to do it, which is to return one at the left, like an overflow whose left subtree is a 2 node, who's rooted at a 2 node, and with the element 2, and the right subtree is a 3 node, so it would be 3 and 4, and T, and this one go there, and that one go there. Okay, so let's implement that. Okay, so I here have A, B, L2, C, M2, D, R2, and in both cases, in the case of TI, you will return an overflow with a 2 or 3 node like now, the one I showed. So I'll just choose the first option. So you return that.
that should just be a T, and then the element here should be C, and then the second subtree would be M2, MD, and R2. Okay. And for the overflow case, sorry I forgot to draw it there. So you would return. So you have an overflow and a tree 1, an element and a tree 2. Okay, and then you will also return an overflow. This one will be 1, 2. So the same left subtree, but with the right subtree replaced with T1. And then this is E, and then you'll have 3 and 4, and then T2, and then the other two subtrees of the 3 and 4 nodes as they are. Okay. So here you have an E, for example. Okay. Okay, so that should be it. And as you can see there, we have the warning about the cases that we left, but we left those cases because we assume that the trees are of equal height. Okay. So now what I will do is try to prove the first lemma. And I actually here on purpose wrote those hints to address your questions about how to use the automatic proofs versus ISAR proofs. So unfortunately, automated proofs take a lot of trial and error and guessing. But in the worst case, if you try to do an automatic proof and then something breaks and then your proof doesn't go through, you can really debug that by writing an entire ISAR proof and then consider all the cases in that ISAR proof, and then if there's a bug in your definition, you'll discover it in one of the cases. What I try to do is to avoid that and try to guess from the sub-goal which case it was by showing you. I'm trying to show you how I do that, but in the worst case, the systematic way to do that is doing the case analysis manually on ISAR, but that would be quite long. So let us try to prove the first lemma. Okay, and see, I will try to do it with the automation. Okay. Okay, so here we have a box there. Okay, so that's it. So what we can do there, this is a function that is defined recursively on two inputs, so you can do it by induction on using computational induction, but with the rule that came out of the recursive definition. So I'll just say here join.induct, and I'll apply auto and see what happens. So here we need to do case splits on the type up I. Okay, so auto split up I splits, and now we have those subgoals. So what do we have there? So the induction hypothesis here. Talks about x1. So the induction hypothesis talks about x1, but we don't seem to have any of the assumption of the completeness. Ah, yeah, because we should have them using sums like that. So now we have one sub-goal remaining. So here we have one more case. So it seems like we have a bug there. So I will try and nitpick to see if we can get any useful information there. Yeah, okay, so we need to find the case. So one way to do that is by the right case where there is the bug. So one way to do that is by just doing an explicit is-are proof that explores all the cases separately. But I will just show you a hack, which I think I showed you earlier, that can just get you basically to discover where's the case. So if you're suspecting that this is the wrong case, for instance, you can just undefined and then see if that changes your goal. So actually that, in this case, this is our main sub-goal. So you can just continuously, but which one inside here? So we can, for instance, try that and see if that helps us. No. So we still have the first sub-goal. Actually, it's clear from the sub-goal that what we were looking for is when the return result is ti, which is this case. So we have a bug in this case. So R1 and L2, okay, you're joining them, and then you get N1 and A, and put it there, and then T, and then B and L2. Yeah, that should be R2. Okay, that does it. But in general, in the worst case, you might want to do the full is-are proof to discover, to understand where the bug comes from. Okay. So here, as I showed you, like these are a few hands-on hacks. Like you can just replace all the cases one by undefined and see. You can also look into the sub-goal and see whether you can get any clues about the wrong case. But in the worst case, you will need to just do an is-are proof. Second sub-goal, second proof, second lemma is that one. So we want to show that the resulting tree is complete, and by complete, okay, so let's just see what the complete means. Complete basically means balanced. So this is complete if both of the subtrees are complete and their height is the same. And here it's the same. Okay, so the three are complete and the three have the same height. Yeah. So here we want to say that basically it gives us a balanced tree. This join, if the inputs have the same height and they are balanced, then we get the same. Then we get a balanced tree again. Okay, so you can probably just apply the same induction and see. Okay, we need to do the same case splitting. Yeah, that does it. Okay, so we're now done with the join function. So we're done with the first exercise. The second exercise concerns the second exercise concerns the height of these a 2 3 tree, and in particular we want to show that the height, like a lower bound and an upper bound on the tree's height. Okay, so we want to show that its upper bound is it's upper bounded by the logarithm to the base 2, because in the worst case you can have a 2 3 tree whose own with only nodes with only 2 nodes. So in this case it would just be like a binary tree, and its lower bound is in the log 3 is log to the base 3 plus 1, because in the best case scenario you're packing your entire tree is of only of 3 nodes. And of course these boundaries are only for balanced 2 3 trees, or for complete ones where basically it's completely packed. So let's see that. So the upper bound, I think we already have a lemma about the slide there. Okay, so let's just try and find it manually. So we can just do find theorems there. Find theorems. Size